I'm happy to be able to join this last session of this prestigious symposium, and I'm very happy to introduce Matthias Rupp, who's going to talk about machine learning for quantum chemistry. I had to make the check to see whether he's a computational person or whether he's a chemist. And after the talk, I think you'll have to decide what his main identity is. I think the important thing is that we can speak together. But you apparently started out in computational chemistry, went into bioinformatics, and now that you've been focusing on this machine learning and also predicting the features of chemical, not compounds, but characteristics, or...
Well, let's find out.
Let's find out. So, predictions has been part of this machine learning adventure as well. So I'm very happy to hear about this, and we'll give you a shot to let us know more.
Thank you, and welcome. Let us start with 4 problems that have something in common. One of them is high-throughput screening. Imagine you have a database of 10 billion compounds, and you want to find some of them that have the property that interests you. Okay? And sorry, I'm completely computational in this talk, so let's say we can compute this property. But still, it's a problem, right? These are a lot of compounds. So then maybe, let's continue here. Maybe you want to simulate a reaction or a folding phenomenon maybe, and it takes a long time. So you have to do a lot of computations over time. Again, the same problem. Let's say your system that you want to compute is very large. In some sense, it's a similar problem. Let's say you had a method which you can scale with that allows you to compute such large systems. It would scale with the system size still, right? And then maybe less intuitive, but let's say you need a very high level of theory to compute a phenomenon that you're interested in. What all of these share is the problem of having extremely large computational requirements. So you need a lot of compute time. And this is a problem in principle that will not go away if you wait a few years. So let's say you do a density functional theory calculation, and depending on which functional you use, the computational requirements will grow as the 3rd or 4th power of your system size. So if you think about it, if you double your system size, it means you incur an order of magnitude increase in compute time. So it means you can double a few times and then you hit the computational wall. And it will always be like that. That will be a little bit of a moving target, the more compute power increases, but in principle there will always be this limitation of computational cost. And the question is, can we do something about that? And in general, there's no, as in general, the answer is no, there's no silver bullet, but in certain situations, machine learning can be helpful. And this is what my talk is about. So how could this work? So that's the idea. Assume you have to do a lot of calculation that are somehow connected. So correlated inputs, basically. Think of a dynamic simulation. All of your configurations will be strongly correlated over time. Think of a database, maybe think of a combinatorial database, it's more clear maybe then. You have a lot of, let's say, molecules, but they are all structurally related, so there's some correlation there. And what you do if you, for example, compute an energy is, well, you solve a complicated partial differential equation, and you do it for related inputs. And if you push correlated inputs into the same numerical solver, what you will get is correlated outputs. So there is redundancy there, and this redundancy can be exploited by machine learning, which recognizes patterns, right? So that's the basic idea. Here in this sketch, the x-axis is some abstract notion of molecular or material structure. So every, let's say if you do molecules, every molecule is a point on this line. How you define this space is the central question. I'll come back to that. Then y is one or more properties, let's say the energy. And if you do have a lot of points on the x-axis and you compute all the y values, then you get the black line. But this is computationally too demanding, so what you try to do is you do only some of the calculations, the red points, these are your training or reference data, and then you use machine learning, the blue dashed line, to interpolate between your reference calculations. That's the idea. And if you can do it well, and we have seen a few examples already today, with different techniques, Gaussian processes, deep neural networks, then you can get the interpolation error to be on the same scale as the error that your reference method makes anyhow. And then maybe this can be useful. So that's the idea. There's a lot of assumptions in this thing. For example, if you have a finite number of points, the function in between these points can do anything, right? How would you know? So you have to make an additional assumption. Here we make a smoothness assumption. In some sense, given by a regularizer, we find the smoothest function through these points. And it turns out this assumption goes along well with, for example, potential energy surfaces. Then, yeah, of course, yeah, it's crucial how you define this space. We'll come back to that. Then this is different from your force field, let's say. In the force field, maybe you start with all the quantum mechanics, and you make successive simplifications, maybe conceptual ones like Born-Oppenheimer, or maybe more practical, also technical ones, and you arrive in the end at a simplified set of equations, and your physics is in these equations. Here it's not. Here we just fit a very flexible mathematical function to these points. The physics is in your reference calculations. So there are some difference to the usual way you do this game. Okay, so that's the basic idea. Any questions so far? Okay, feel free to interrupt. It's your talk. I know this already, right? So people mention Gaussian process regression a few times. Anatole von Lilienfeld, he says kernel-rich regression, and there are two different methods. One is Bayesian, one is frequentist, but no one cares. I don't care, at least. And as far as the predictions are concerned, they are technically identical even. So I'll use them interchangeably here. But no one really put on the formula, so let's have a look at the formula, right? So in this model, a prediction F for a new, let's say, molecule X is a sum over the n reference calculations that you did. Each one has a regression coefficient, and then there's this function k, which somehow measures similarity, let's say, between the ith training input, the ith molecule from your reference data, and the new one that you want to predict. So what is this doing? So technically, what happens here, this k is a symmetric positive definite function, which corresponds to an inner product in some high-dimensional space, but I don't want to go into that direction today. There's a tutorial where you can read it up in a lot of detail. But what really happens here is this looks like a basis set expansion, right? And in some sense it is. We place a basis function on each training reference calculation and weigh them. So let's have a look at how that works. Here's a 1D toy example. This is the x-axis. Here's the y. This is a function you want to predict. Each training or reference data is one x, let's say one molecule, and a corresponding energy. And then you want to fit this blue line given these points. And what's happened, let's say you put a Gaussian basis function on these points, you sum them up with different weights, and you get the dashed line, which starts mimicking the blue line that you want to learn. So very straightforward. This is called kernel-rich regression or Gaussian process regression, together with the previous slide, let's say. But that's the basic idea. And so this is straightforward. Just put basis functions on your reference calculations. Of course, if you think about it, it's very different from what we usually do, right? So normally we would put basis functions on other quantities, not on a complete calculation, right? So in that sense, it is actually quite different. But that's the basic idea of how you can fit, let's say, energies, for example, as a function of structure. Yes, before we go on, is that fine with you? Okay. So the central point here is, if you remember the sketch, is how do you define the x-axis? How do you turn a bunch of atoms with their position and element type, how do you turn that into, let's say, a vector in a vector space so you can compute a Gaussian basis function, let's say. How do you do that? And that's the key question here. So I call these representations, and I'll come back to this name on the next slide, if I don't forget. So the first observation is, I mentioned before that these okay, these kernel functions k, these correspond to inner products in some space. And if you think of inner products, so Hilbert spaces, the inner product is not uniquely defining a space. Sorry, that was my message that I wanted to give. So if you look at this example here, we have two vectors A, B, and they are mapped to two different spaces. And if you compute the inner product in this space, so you have an AB and an A prime, B prime, you compute the inner product, you get the same expression as if you do it here. But clearly these are different spaces, right? They differ here. So an inner space is not uniquely defining an inner product is not uniquely defining the space in which it lives. And if you transfer that to this setting, then it means there are many ways how you can set up such a space in which molecules live or materials. And or you can define many different representations of them. And that is what actually happened. So there's a these are the, from my point of view, state-of-the-art representations. They're symmetry functions by Jörg Behle. We have one from Jörg's group here. There's the bispectrum and later smooth overlap of atomic positions from Garbocciani in Cambridge. There's moment tensor potentials from Alex Chapeyev from Moscow, Skoltech Moscow. And there's the representations that Anatole von Lilienfeld showed this morning. And very related to our representation, the many-body tensor representation, which is the one I will briefly show here. And now, only very recently this year, pioneered by Michele Ceriotti from EPFL, people have started also formally developing a mathematical framework that connects these different representations and allows, will eventually allow us to understand how these really work, how they are different from each other, and what the relations are. So, a word about representations. So I use the word representation to distinguish from descriptors. We saw a lot of examples today also where people use only a small bunch of numbers to describe a molecule. This is fair and the right tool for some applications, but if you want to predict properties like the energy or maybe a polarizability or a property that depends really on the atomic coordinates, then you have specific requirements, and such coarse graining descriptors are inappropriate for this type of models. In particular, you should be invariant, the representation should be invariant against any transformation that doesn't change the property. If you have your molecule here, you translate it to here, energy is the same, your representation must not change, must not depend on the lab frame, for example. Same for rotation, must not change the property. Reflection depends on what you're doing. On the other hand, anything that does change the property, your representation needs to reflect. It needs to be unique in the sense that otherwise you have a problem. If you have molecule A and with one energy, molecule B with another energy, they have the same representation, but the machine cannot tell them apart. It can only predict one value, and it will have immediately a minimum error that you cannot get below. So this is a necessary requirement. My goodness. Okay, I'll speed up a little bit. It should be smooth for the machine learning. It should be general. It should be fast to compute. Electron density is a great representation, but if you have computed that, well, you have done all the work, so that's pointless for the machine learning then. And it should be simple from my own point of view. So what's the many-body tensor representation? How does it work? Look at this toy example. I look at k-body terms, but stratified by chemical element species. So that, for example, let's look at inverse distance here. We have one inverse distance between the two hydrogens here, so one peak, not a delta, but a Gaussian, because we need a smooth measure of similarity. We have two HO distances, which give slightly higher peak here, and no oxygen, so nothing here, and that's all the combinations. And if you sum these up, also if you put these into the same plot, you get this nice kind of spectrum-like representation of a molecule. That's the idea. Let's not get into the formula for reasons of time. If you do this thing, this is for a bit larger molecule, formic acid. Still, it's very clear what these peaks are and and what they signify. Same thing now for a three-body term for angles. Still, you can you can still look at this plot and understand something. This is a distance plot for aspirin, so a bit actually pharmaceutically relevant molecule. And you can do the same trick for materials, so for periodic systems. This is SALT FCC. I will not go into how to adapt the many-body tensor for the periodic systems. Let's spend the time on some results instead. But this is a pretty simple, pretty straightforward idea, and it works remarkably well. What I'm interested in, I want to make predictions. I don't do simulations. Other people, so dynamic simulations, I let other people do that. Here in this sketch, let's say this is the potential energy surface of a single system, let's say one molecule. And then if you do, let's say, dynamics, then your hope is that if you have done these calculations already, this information should help you calculate the energy here. And now if you have many systems, let's say this is potential energy surface of another system, another molecule, then the hope is that knowing these points, if the two molecules are similar, will also help you predict this point. So I want to go across systems. So let's say, for example, to screen databases, to design materials like in the previous speaker's talk. Very brief here, I just want to give you a rough idea of how accurate this is. This is all retrospective benchmarking, not an application. If we predict the atomization energy of small organic molecules in their ground state, then we get errors of less than a kcal per mole, which is, I think, reasonable. Then you can start thinking about if you can do useful things with that. Of course, I should show a learning curve like Anatoly did. I will in the future, I just don't have it on this slide. This is similar data, just don't pay attention to this. It's basically showing that for dynamic simulations, it also works compared to the literature. This is maybe a bit more interesting. This is from a machine learning challenge that we organized, also the institute I am in organized, Christopher Sutton mostly, on Kaggle, a website dedicated to challenges. And we gave here structures of approximate geometries of aluminum, gallium, indium sesquioxides. So this is already a realistic kind of material space. These are interesting as transparent conducting oxides. And what we gave is the Vegat's rule geometry, so a rough first guess of the geometry, and the energy you would get if you would relax this geometry to the minimum. So the quantity we are interested in, but starting from a cheap surrogate of the geometry that is fast to you can compute fast. So there's an additional error in the inputs if you want, some noise on the axis. So what we get here are errors of about 30 millielectron volt per atom for the energy and about 200 millieV for the band gap, which is reasonable given that we have the error on the geometries. If we do this with the correct geometries, with the relaxed ones, then this error goes down to below 10. For this type of complex system with only 3,000 structures, this is quite good. And I wasn't competing because I was part of the organizing team, right? But we still put our models in to see how well they performed, and I am happy, let's say. Yeah, in the interest of time, let's continue. These are again scatter plots, DFT energy, the predicted energy with our model. Here's with the approximate geometries, with the actual geometries. And you can see here the colors are the different space groups. And you can see that, for example, here, this space group 227 is harder to predict for some reason than the other ones. And this is something we are still looking into and trying to understand what exactly is going on here. And finally, this is current ongoing work on the archive with Gus Hart et al. Here, we try to create a materials data set, which is a bit similar to this QM7 or data set for the molecules. These are binary alloys. You see them here. And these are not in their ground state anymore. These are 3 different symmetries, FCC, HCP, and BCC, and all the possible unit cells up to 8 atoms. So basically a kind of semi-comprehensive sampling of these small unit cells for these binary alloys. And 2 things here. You see that some of them we can predict very well with an error of about 1 millielectron volt per atom, which is my personal goal. Some a bit worse. The worst one, 20 millieV per atom. We don't know why. At the moment, we are still figuring this out. Could be anything. Could be a problem with the pseudopotentials or a problem in the way the data was generated. It could be that it's just harder to learn. It could be that the niobium nickel is just being able to do more things than the others, and that would make it harder to learn as well. Let's see. Point here in this study is that what you see here is if we train individual models on one binary alloy data set, and then I take 3 of them, 4, 5, and at the end all of them, and put them into the same data set, just train the model again. What you see here is the deviation in error from the deviation in mean absolute error on the combined set from the mean of the mean absolute error of the individual sets. So in other words, is the difference I get, the additional error I get if I pool unrelated data. And you see that it's basically none. If you look at the scale. So what this shows is that this type of model can accommodate basically, I don't want to say arbitrary data, but you can take different systems, put them in the same data set, and don't worry. And this is, for example, quite different from, let's say, cluster expansion, which has been the traditional way to do this. Yeah. So where do we want to go with that? So I'm trying with this modeling approach, with machine learning approach, to go to crystal structure prediction. What do we need for crystal structure prediction? Well, we need a sample. So we want to find out for a given system what are the stable and metastable states that you can find it in. This is interesting, for example, in a variety of areas. If you do molecular crystals for formulation and pharma, for example, but also for materials, of course. Basically, it's finding all the low-lying minima on a high-dimensional function surface. So we need a sampler which gives us candidate structures, and then instead of for each structure doing the ab initio and relaxing it and getting the energy, we put the machine learning in between, which is a lot faster. So we need about 50 to 100 milliseconds per prediction, which if you scale it up, also extrapolate it, is about, I think, 1 million predictions per core per day or something like that. So it's reasonably fast to screen large spaces. And only when the machine cannot do the prediction, it should resort and do ab initio calculations in an automated fashion. What you need for that is, of course, a way to tell when should I make a prediction, when should I do a reference calculation. So you need an uncertainty estimate for individual predictions. Until recently, we were not able to do that quantitatively. Qualitatively, yes, but quantitatively, no. There's a natural measure for our models. It's the predictive variance of the Gaussian process. But now, finally, thanks to a student, Marcel Lange, we get reasonable uncertainty estimates, so quantitative ones. This is the log predictive variance, your uncertainty estimate. The more to the left, the more certain. And this is the error for each prediction. And you see that if the model is certain, the error is always low. Here, yeah, well, you just don't know. The uncertainty is high. And previous plots were more like, had more points here, some outliers. And so it was OK, but it was not really the way what we wanted. Now, finally, it seems to work better after investing some work. Well, we need an efficient implementation. I'll show that on the last slide. And yeah, we are closer to this goal, let's say. Not there, but we are getting there. Okay, with that, I'd like to briefly recap. I talked about the idea of using these machine learning models to interpolate between electronic structure calculations, exploiting redundancy, saving computational time, a lot of it. About the representations, I showed the many-body tensor representations. This is at the heart of these methods, and some examples of energy predictions. I'd like to thank the group and funding. And finally, I would like to point out, there's a tutorial if you want to know more about the method. I took great pains to write this in an understandable fashion, hopefully successfully. There's a special issue of on a data-driven theoretical chemistry from Journal of Chemical Physics, about, I think, 43 contributions. So you get a nice cross-section of this community, and our editorial gives a 1-paragraph summary of each contribution, so you can hopefully quickly go through it and sift out the ones that are interesting to you. There is sufficient code in C++. This is a handcraft, so the important parts are handcrafted, the rest is Python bindings. This will be released eventually. If you want to try it out now, just write me an informal email. I'll give you access immediately, no problem. It will go online anyway in maybe early next year or late this year. So just, you can try things out here. It's really easy. I can send you a tutorial as well, and you can just get started. And then finally, I would like to point out this site. It's a very low-key site, so no fancy design here, but it provides data sets that you can basically download that have been used by people to benchmark. Yeah. So you can just download data sets here in a format that is easy to parse, and these three things together hopefully will enable you to just try this out if you feel that it could be useful or interesting to you. And with that, I'd like to thank you for your attention.
Thank you very much. Do we have any questions?
Yes. Yes. Yeah. Yes. So it depends on your definition of requirement, but let's just take a look, right? It's easy to see what I mean. I say these are strict requirements, and the reason I say that is, let's say you don't have invariance through translation. Okay, then you put your molecule in your Cartesian coordinates and give the machine learning algorithm the energy of this molecule. Now you take the same input maybe from your lab colleague, but here it's not here in the Cartesian space, it's here. And for the machine learning algorithm, because you use Cartesian coordinates, these will be two unrelated systems. So you have to make the machine learn this invariance from the data by providing the same molecule in different places. You can do it, but it will cost you an order of magnitude more reference calculations. And the same holds for these other things. So this is why I say these are strict requirements. Requirement 2, you need, if you want, in principle, your error to go to 0. Of course, in practice, you might say, hey, I'm okay with whatever 5 kcal per mole. I will do it a bit more coarse-grained. That's perfectly fine. It's just if you want to be as accurate as possible. So my goal is to use as few reference calculations as possible, because that's what I want to save, right? It's also why I don't use neural networks, but kernel learning. And for this goal, I need these properties. But of course, I mean, there's no law, right? So which slide? Yes. Yes, it sounds like, but it's just, it's easy to resolve. So usually these methods are applied for noisy data. And if you think about it, let's think of just fitting a line, because this is what happens in the end, just in a very high dimensional complicated space. Right, so if you have no noise and you give me 2 points, I will give you this and claim 0 error. That's what I'm trying to do, because we have no noise. Okay, very strictly speaking, we have some minor noise from numerical convergence issues in the let's say DFT. But that's it, right? Now, if you have noisy data, of course, you will have you will have different values, right? And now, I can still put the line here. And if you give me infinitely many data, it will be the correct line, just as here. But you can never measure it, because all you have access to are these noisy points. So you can never go there. And this is why they say that. And they are right in their setting, but I don't have noise. So I can claim convergence. Of course, in practice, we don't converge to 0. We would need way too much data for that. The law is, it's a negative, the error decays asymptotically as a negative power of the training set size. So that means, sorry? So say again, please. Yeah. Yes, at infinity, exactly. But what I'm saying is that the convergence rate is exponential. So you would need unreasonably large training sets to get the error basically to whatever, an arbitrary small number. But what we are trying to do is in the what I'm trying to do is in the small sample regime, and we have maybe, there was this challenge by von Lilienfeld, right? 100 reference atoms, molecules you can choose and get the error to a kcal per mole. this is a pretty strong challenge, I would say. But yeah, that's what we're trying to do. Use few reference calculations and get the error as low as we can. How far we can lower it? Let's find out. So yes, I agree. Funny enough, one of the most influential papers by Chani on the Gaussian approximation potentials, 2010, I believe, the title was but the reference calculation does, of course, right? So that's one of the many aspects which I hinted at in the beginning, how this is different from your usual fitting, right? In the molecular mechanics, you have no explicit electrons, and you will not get the effect of, I mean, you can try to get a little bit indirectly, but that's it. But here, yes, we don't have the electrons, but indirectly we have them, right? We may, of course, there are assumptions in there, like they are heavy, the electrons are less, blah, 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 blah. But still, in principle, we do have these effects here. Now people are also starting to go explicitly for excited states, for example. Entanglement is another very interesting direction, and we have, yeah, but I don't want to talk about that yet. So people are going into these directions, let's say, where you have effects which very strongly depend on let's say, for strongly correlated systems, for example, right? If let's say here, if you have an energy model which is based on atomic contributions, which maybe not here, but other people do, then this works, of course, nicely if you don't have too much dependence on the whole system, right? But if you have a strongly correlated system, that might become harder. So, well, people now start, now we have done these basics, now people start and go for the more challenging problems, right? Yeah, so but that's currently happening at this very moment. Let's see where it ends.
All right, I think we need to break off for the next speaker. Thank you very much, and thanks for the nice discussion. And now we have Thomas Schön, who's going to discuss more about machine learning. And you're from the IT department of Uppsala University, so you're one of our local representatives. And also not a chemist, but a computational scientist, if I understand it correctly. Very good. So thanks for coming.
All right, good afternoon. So I'm going to talk to you a bit about machine learning. And I've heard much more than I thought I would hear about machine learning today, which is very good. And I'm glad to see that you're really pushing it. And I spoke to Marcus during lunch. I think he went home. And he reassured me that so I was a bit impressed that there were so many people. Oh, there you are. So many people doing this in your field. But then he said, but there are not so many actually. It's basically you in this room and a few more, if that's correct. But I think that will change. I think you are on the right path. I'm extremely biased here, obviously, but it makes what you have been talking about here makes a lot of sense in my ears. So I'll say a few words about the field itself, which is the field I work in. before doing that, so this is with a lot of people talking about AI and machine learning and so on. So I like this quote in this setting, which is good to keep in the back of your mind when we're talking about things that are fairly hyped at this moment. Still, it has good things to offer, but it's not going to solve everything straight away, that's for sure. So I'll say a few words what we do in my team, just so you know a bit about the background, the type of problems that I look at. So we're trying to automate the extraction of some knowledge or understanding from data that we measure. And the strategy we have is to do both basic research, where we develop new theory, new methods, and to do applied research that I do together with companies or applied research groups in various areas. And here are a few examples of companies I've been working with and work with at the moment. So this is a product that's being built by a Swedish company called Elekta, which is for radiation treatment of cancer. So there you have a real-time MR camera, so you can measure in real time what's happening in the patient. That means you can track the tumor, and in real time you will then, hopefully that's our job, to make sure that you can adapt the radiation and follow the tumor. As opposed to today, where you do one measurement and then the person goes into the radiation treatment, and then you have repeated radiation treatments without measurement, so to speak. So this is happening, and then this is the Swedish fighter aircraft built by Gripen. So we looked at the navigation system for that aircraft. I'll use this a little bit today just to illustrate a few concepts, which is motion tracking. So human motion as I walk around, computing in real time the position and orientation of the human body, which can then be used for the movie industry and the gaming industry, for example, but there are also other applications. And autonomous cars, together with this company on the Swedish west coast, nowadays mainly together with Autoliv and Veoneer, actually. So what we do is we build probabilistic models of these dynamical systems and their surroundings. And then we use the data that we have to learn these models. And why? Well, because either we or the machines need to understand what it is that's happening. Maybe that's enough to understand the situation. Sometimes you also want to go in and affect the situation, to change something. Like in a car, for example. When you're driving a car, then you're constantly changing the situation. That's what the machine will do. So that's what we're doing. So what's machine learning all about? Well, in one sentence, it's about learning and reasoning and acting based on data. And it's a bit of an emphasis on this one, that you're learning without being explicitly programmed for that task. And if you want to, like, executive summaries, I like these two papers by Subin and Mike on the area. They're a few years old, but they're still like 5-page versions of good snapshots, I think. I'll put the slides on my website if you want them. They will be there anyway, I guess. So the 4 cornerstones that we have is data, and typically we need a lot of it. But it's also interesting to consider cases where you have few data, but most of the methods require quite a lot of data. After that, you need a mathematical model of some sort, or a representation. So I'll come back and say a few words about that. Once you have those things in place, then you need a way of transforming the data into your model to figure out the parameters. So that's a learning algorithm or estimation algorithm or inference or whichever word you use. And sometimes we also have a decision stage or a control stage where we actually intervene and control the situation. And this has also been discussed quite a lot today already, which representation we should use or which mathematical model. That will affect everything. So if you pick the wrong representation, then there is no algorithm to help you out later on. So that needs to be done carefully. And there's even a conference now, since this is heavily driven by the deep learning revolution, I would say, but an entire conference dedicated to suitable representations for learning what's happening. Okay, let me make it a bit more concrete what I mean by a mathematical model. So this is more of a classic example, not necessarily what we do in machine learning, but yet to get a feel for a mathematical model. So we consider the problem that we want to figure out what is the position and the orientation of my body as I move around here. And the sensors that we use for that are inertial sensors, like the ones you have in your phone. So we have 17 of those that we place on the body together with ultra-wideband, because those sensors will not give you a good position estimate. And since we are in this setting indoors, I can't use the GPS, so I need something else to get the absolute position. So then we can use ultra-wideband. And then the challenge is that we need to learn some unknown parameters here. We all have different body shapes, so we need to learn that first. And then once we have that, we need to figure out what the position and orientations are. So in order to do that, we're gonna show you what happens when we use 3 different kinds of models here. So the first one is a very simple one, which is just using the basic IDs from physics, just integrate the measurements that you get. So from the measurement you get angular velocities, so we can integrate that to an angle. And I also get accelerations, or the specific force actually, because I cannot remove gravity. So it's gravity plus the acceleration that's happening. And that I can double integrate to a position if everything was perfect. So let's see what happens if I do that in an experiment. So we have this situation, a person walking around. And then I just do what I just said, and the following thing happens. And this is not obviously what happened to that person. so he's still nice and fine. And why is that happening? Well, because I used the wrong model for the thing, right? So no matter how hard I try with that model, it will not work, because I told it too little based on the data I used. So it's impossible to solve the task. So then we go back and we think a bit. What else could I tell about the system? Because I know this system quite well, because I am the system. And one thing I know is that my upper arm is connected to the shoulder, and so on. So let us just tell the model that simple fact. So that's, in a fancy word, that's called a biomechanical model. So if we do that and see what happens instead, we get the following situation. So this is now starting to look a bit better. I think, yeah, you can see it there. But it's still not perfect, because the probability of that person sinking through the floor is exactly the same as the probability of me sinking through the floor here. So that's not going to happen, right? So what's the problem? Well, it's my problem again. I did not tell the model that there is a floor. So let's tell the model that there is a floor and see what happens. And now it starts to look a bit more reasonable. So this is what I mean by you should really think carefully about the model, as we have been discussing throughout the day, because if we get that wrong, it doesn't matter what you do after that. And what I showed you there is something people can buy and use. But to really get it right, you also need something else, which you couldn't see, because this was in well, it was a real human motion, but still I showed it in an animated thing. But what you would see if I showed you that in this room is that the person would be drifting away, because here I use no absolute information. So if we bring that in, and I'll show you from a lab experiment, you get something that looks like that. So our estimate of the position and orientation is this skeleton that you see. It's not perfect, but it's okay. It's definitely enough for many applications, not for every application, but for quite a few. So for the movie industry, for example, or the gaming industry, this is perfectly fine. And just to so you have competing. Let's skip that for a little while. Competing technologies where you use cameras instead, which also work really well. You can get extremely high accuracy with camera-based systems. But of course, when we do this in a camera-based system, you can still you can see what the person is doing. But of course, with our sensors, we can do that because they don't rely on a line of sight. All right, let's skip that. Yes, of course. Yeah, that's very good. So the question is, when I add the constraints, don't I explicitly build the model? Absolutely. So that's why this is not the well, that's why I wrote a more classic example. So this is not the typical machine learning way of solving the problem. This is more a classical engineering way of solving the problem, so to speak. So I mainly include. So it's a great question, especially glad that you asked it now. So in machine learning, what we typically do there, we play the game that we don't know, and we use the data and hope that that is enough to figure out what goes on. So the reason I showed this was mainly to get the feeling for a mathematical model, and perhaps also to respect the problem that based on data, it's quite hard to learn everything, right? And I also believe that it makes a lot of sense to actually use stuff that we do know. There is no reason to learn everything from data. If you know fundamental things, why not use that together with the data to learn the new things that you don't know? There is no reason to relearn everything, so to speak. So let me show you an example that's a bit closer to the machine learning side. So here we're doing what I said. So we used the data, but I also used physics. So Maxwell taught us about magnetic fields. So here we built, we are playing the game of building a model of how the Earth's magnetic field is distorted in a building. So in here, for example, this is a super interesting area in terms of the magnetic field because you have a lot of metal structure. So the Earth's magnetic field is severely distorted. And then in the floor, there will also be metal things, I'm pretty sure. So it's a magnetically super interesting area. So why would I want to do this? So we had this idea that if you have a map of how the Earth's magnetic field is distorted, almost all of you, many of you, actually have the hardware in your pocket or wherever you keep your smartphone to position yourself because you have a magnetometer in there sensing the magnetic field. So that's for free. And with this solution that we are almost done with, we can position people indoors with a few meters accuracy. Because it's exactly the same principle you used in the good old days when you had a piece of paper and when you came to a new city like Uppsala, and then you looked at the map and you looked at real world, and if you couldn't find where you were, you just walked to another position and observed a few more things, and then you know where you are. Nowadays you use your GPS, I guess, but that's also fine. But that's just one map, right? There's so many other maps, and we've been talking about a few different maps here in the world of chemistry as well. And I think that idea is really extremely useful. We can build maps of all sorts of things, for example, the magnetic field. So, and here we're using a Gaussian process that's been discussed a bit today. I'm going to talk a bit more about that later on. To build a map of the magnetic field, and that Gaussian process is such that it will obey Maxwell's equations, which I think is pretty cool. Unfortunately, it did not improve the result too much in this case, actually, from just using the Gaussian process. But still, it is possible to include basic knowledge into the model itself sometimes. So to be more precise, any linear operator constraint can be pulled into a Gaussian process. And what is a linear operator? That's a fancy word for a linear combination, for example, or a differential equation or an integral. They are all linear operators. Let me show you what it looks like. So this is from a toy experiment together with some friends in Alto. So what you have here is a little robot driving around, and the little snake thing popping out at the end. That's so the magnetic field, that's a vector field. So I'm just showing you the norm of that. So the value of the strength of the magnetic field at that point. And as you can see, as it's driving around, it's gathering more and more information, and it affects its neighbors because there is a spatial dependency via the Gaussian process. And as you can see, it's an informative map. If this was all one color, it wouldn't help. But this is, we probably don't need that. It's definitely changing as we go, hence we can use it and actually figure out where we are. So those were two examples. What we need to do in order to build these models, we need to do a few fundamental things. And computing the the model, learning the model, if you like, or estimating the parameters, always involves solving integration problems and optimization problems, or one of the two. So integration problems are typically in the form of high-dimensional integrals because we are marginalizing, as it's called. So we are integrating over some of the variables to get rid of them. So that's something that we keep doing all the time. Optimization to extract point estimates. So we often want a full probabilistic representation of the model, but sometimes it's required to provide a point estimate, and then we usually solve an optimization problem. And these problems are most often we cannot do them in closed form, so we are forced towards approximations. And that's okay. We can do all sorts of things, and we have mentioned Monte Carlo methods. So we work quite a lot of sequential Monte Carlo, for example. Or you can do variational inference, which is heavily used in machine learning at the moment, where you postulate a model class and then optimize the parameters in it. Stochastic optimization is used a lot. So whenever you do deep learning, you typically use stochastic optimization to find the optimum. So the key lesson I've learned over the last 5 years in machine learning is, which resonates very well with what you have been talking about here today, is that flexible models offers the best performance. So what do I mean by a flexible model is the next question. So how can we do that? So there are a few different ways. One way is to use models that have a lot of free parameters. You fix the number beforehand, but they are a lot of them, a very flexible function expansion. That's what deep learning is all about. And that's called a parametric model. Another way of doing it is what you've been talking about here today, a Gaussian process. Then, as soon as you get a new measurement, you get effectively a new parameter in the model. Hence, they are called non-parametric. Maybe not the best name, because you just get more and more parameters, but that's what it's called. And the Gaussian process is one member of a family of models called Bayesian non-parametrics. So there are other processes that can be used. The Dirichlet process, if you have discrete events, for example, and beta processes, and so on, and you can invent your own process. And this is sort of related to your question here. So if we don't know what's going on and the data is to inform us about it, then the data should have quite a lot of freedom in the model, fluffily speaking now. So if we restrict it too much from the beginning, then it has no chance before it even tried to start, so to speak. All right. So what I'll try to do now is I'll say a few words about what I think is the key thing in deep learning. What's that all about? Well, what is it? And then I'll say a few words about Gaussian processes and what that is, which will be, luckily we did not coordinate before, Matthias and I, but it will be a different take on it, so that's hopefully useful. And then, if I have time, a few other trends tools happening. I'll say a few words about the project that I'm part of here in Sweden called WASP, and then I'll conclude after that. All right, so deep learning, what's that all about? The mathematical model itself is not new. It's been around for 70 years, at least. But in the recent years, as you all know, there's been sort of a revolution. I think we can use such a strong word in this situation. And why is that? A few different reasons. We have a lot of data, better, faster computers, and an enormous, absolutely enormous industrial interest. And there's been some methodological breakthroughs as well. So the underlying model is just a huge nonlinear function, which is built in such a way so you have several layers of abstraction inside it, if you like. And the parameter values are then automatically trained by solving an optimization problem. So there is a limited amount of engineering going on. There's still a fine art of knowing which structure to use and so on. But apart from that, the exact features, if we call them that, are learned automatically, which is the nice thing about it. So this model is called a neural network. And what it is, it comes down to linear regression. So you just do a linear regression from your input. So you get an output y. And then you wrap that through a nonlinear function, and then you do another linear regression, wrap it through another nonlinearity, and that's it. It's nothing else. And then you can bring in some structure on the exact form of these regularizations, and you can use different nonlinearities and so on, and then you call these things different things, but that's basically what it's all about. So you can think about the model as a sequential construction of generalized linear regressions. And then, so the cool thing about this is that when you throw a lot of data at this, it's doing surprisingly well in explaining that data. And at this point, no one can explain why that actually happens, which I find quite fascinating. And I guess it's sort of the stage we were 300 years ago when we're using differential equations. So then we know very little about differential equations, but people started understanding that, hey, differential equations, that's a cool tool to describe the world surrounding us. And they started using it to do all sorts of things, as you know. And then later on, so by now we have a really solid theory explaining how these differential equations behave and their properties and so on. Here I don't know, maybe it's a strong analogy, but we're sort of in the similar situation where we know that this thing works, but we can still not properly explain why. Now that's a problem for me and people like us to figure out why that is actually working. But in an applied sense, it does work. So it's a useful tool in that sense. To some problems, not to all problems, for sure. Yeah, let me skip a bit of that. Let me show an example which I think is interesting. So this is from Medicine. It was published some time ago now, and it's about classifying these little dots that some of us have on our skin. So people like me who are a bit sensitive to the sun should have a look at those and make sure that they are not developing into something dangerous, indicating skin cancer, for example, or something else. So and then you go to a medical doctor who is trained and will look at that and tell you what's happening, and they are extremely good at that. So the idea they had in this paper was instead, let's show one of these models a lot of examples. No, actually, it's not that many. It's 130,000 clinical images. But there is also an idea here which is transfer learning. So first you start with a model that's been looking at 1.28 million images, just all sorts of different images, and you train a model from that. And then you start from that model and show it these 130,000 images of skin lesions and use that model. And then you feed in some unseen data into the model, and it'll spit out a prediction of what's going on. And the interesting thing is that this, on skin cancer, this performs on par, slightly better than professional dermatologists, which I find interesting. That's not going to change the world for dermatologists, for sure, but it's, as someone said, it gives you reason to at least be, what did they say, to remain cautiously optimistic about these tools, that you could actually use this. And we have recently done working on this for, I have no slide on that, we haven't published it yet, but on ECG, electrocardiogram, doing investigations on your heart, where when we compare to professional cardiologists, get on 5 of the 6 most common conditions with the human heart, or failures, get on par or slightly better than medical doctors. But again, that's not solving the entire situation, but it helps a little bit maybe. So that's the deep learning side of things. I'll say a few words about swap to the different model type and talk a bit about the Gaussian process. So what is it and why is it used everywhere? well, it's not used everywhere, but it's used in quite a few places, and I'm pretty sure it can be used in quite a few more places. So I'm using it more and more. And why is that? Well, it's because it is a model of a nonlinear function. And nonlinear functions pops up all over the shop, and we often want to understand them and learn them from data. And its representation is non-parametric and it's probabilistic. So it means, and you have been stressing that quite a lot throughout the day as well, which I find interesting, so that you can also quantify a bit what you don't know. Not only what you know, but to some extent what you don't know. And then maybe you can use that to do exploration or figure out things that maybe you didn't know that you didn't know, so to speak. That's the really interesting parts if we can get to that. So what is it? Well, let's phrase it in terms of an abstract idea. So again, falling back on linear regression. So if you do probabilistic or Bayesian linear regression, then you're looking for what's the distribution of the unknown parameters based on the measurement. So that's the object that you're looking for. But the situation is often that this linear approximation of the function you're after is already too strong, and what you would want is actually the function itself. So what you could do instead is to ask the question, what if I, rather than putting a prior on this, or putting some assumption on this unknown parameter, what if I put a prior on the function itself and search over the function space? So looking for what's the distribution of the unknown function given the data I have. What if we could do that? That's what, so this is abstractly put, but this is what the GP provides to you. So let's see if we can make that a bit more concrete. That was extremely abstract. So if I want to build a distribution over functions, one way in which I could envision doing it, maybe the simplest way, is to say if I evaluate this function at some point x and another point x prime, and then I assume that they are jointly Gaussian distributed. That's arguably one of the simplest models we could come up with. So if you agree that that would be okay, maybe you don't agree that's the best, that's not necessary, just that it's okay, then we can of course do this for any finite number of input points. And that's it, that's what the Gaussian process is. So it corresponds to assuming that any finite, when you look at the construction at a finite subset of points, then they are jointly Gaussian distributed. So that means you have a prior over functions, actually. So if we look at the little toy example with one input and one output, and then as a prior, I say I have a mean value function of 0, and then you can imagine, hopefully, the ridge using my fading color scheme here, which is the assumption you make on the kernel. And then, since it's a generative model, I can generate examples from this model. So I generated 5 different examples from this particular model. And then what you want to do is, of course, to populate this with data. This has no data, so it's useless, right? So you need to somehow put the data in there. And if we do that, let's see what happens. This is still the prior. And then the game we're playing is we're trying to learn this black curve underlying, which is clearly a nonlinear function. And then as soon as you give me one measurement, I'm going to incorporate that measurement into this model and update it sequentially. So when you gave me this measurement, what happened is that, of course, I gained a lot of information about the underlying function in that point. But over here, it doesn't help because it's far away. But close to that area, I can probably bring down the uncertainty a little bit, according to the assumptions I've made on the model. And then, as you gain more and more information, you reduce the uncertainty, and you get more and more information about the underlying function. And these dashed lines or curves, they are draws from the current model with these 3 measurements in it. And then as we tick along, of course, we get more and more information and understand the situation better and better. And interestingly, we also know a bit about what we don't know. So if you are now in charge of which experiment to carry out, you would probably not carry out an experiment over here, because you know that you know what's happening over there. At the same time, you know that you're highly uncertain over here, so maybe it's worth doing an experiment over here, or perhaps here. So you have some understanding of that, which can be helpful. How are we doing on time? So I'll say a few words about a few other trends I see in the area that's happening. One of them is something called probabilistic numerics, which is maybe not so interesting in terms of applications to chemistry, but in terms of building new algorithms, I think this is super interesting. So we are reinterpreting basic numerical tasks in terms of probabilistic inference. And it's not like, oh, they sort of look the same, they are exactly the same. So you can take, for example, I'm not sure if you're familiar with an BFTS for solving nonlinear optimization. So if you have a nonlinear optimization problem and you want to solve that using a numerical algorithm, one of the algorithms for that is BFTS, after Löwdin, Fletcher, Goldfarb, and Shannon, who invented that in the end of the 60s. It's a really cool and useful method. That has been shown to be equivalent to putting a very specific prior on the parameters and then doing maximum posteriori estimate. That's it. And when you look at the shape of that prior, which a friend of mine at Max Planck, Philip Henning, has done, that looks really weird, but that's okay. But that gives you the idea, why should I use that prior? The reason they did it back then is super clear, because they did not have these fancy computers we have. So it's a beautiful construction when you put yourself back in the end of the 60s, because it used very little memory, it used very little compute. That's why they choose it in that way. But today, why should I choose it in that way? Maybe because I have these things, right? So maybe I can choose it in a different way, and you can. So this we have used to derive new algorithms along that line. And you can do similar ideas for others. So this is a great, for me at least, inspiration for new algorithms. And if you find that interesting, then Philip and some of his friends wrote a really nice paper just gently outlining this idea in some more detail. So I think we will see much more coming out of this idea. Probabilistic programming is another thing that we work with quite a lot across the street these days. So what we're doing there is we're using computer programs to represent the models. And this, we still need to properly prove that this is the case, but I think this will give us access to a wider class of models compared to using, for example, graphical models only. So this is wider in the sense you can have recursions and so on. And it's a super interesting combination of fields. I think we should do as much as we can to tear down these walls between the fields, like what we're doing during these days, I think, which is great. And this is one attempt between people building programming languages and people doing machine learning and statistics, so managed to come together and do some really cool things, I think. So we have built our own language, which is specifically built for dynamical systems and doing inference in those. It's called Birch, if you want to have a look. We have a pre-release. It has its own compiler, and it can do simple things so far. Well, let's skip through these things. SMC is an area, it's a fairly niche area, but where I've been working a lot myself, which is providing approximate solutions to integration problems when you have some kind of sequential structure present. For example, when you have dynamics, you have a sequential structure over time, but you can have it over space or whatever. I'll not say much more about that. I'll say a few words about variational inference, because if you find yourself in the situation where you want to compute a posterior or a distribution that's unknown, then either you can do it via solving integrals, or you can use variational inference, where you postulate, I'm guessing that it sits within this family of functions, and then you solve for the unknown parameters. So you have less guarantees of convergence, but it works fantastically well, I must say. For someone doing a lot of Monte Carlo, I was quite surprised when I first started implementing this in terms of what it can give you. So let me wrap. I'll say a few words. I was asked to say a few words about this project that I'm part of, which is VAS, which is funded by a foundation here in Sweden called Wallenberg, which is a private organization from a family. So it's Wallenberg AI Autonomous Systems and Software program, which is, it's actually the largest individual research program in this country. And the vision here is so Sweden is a bit behind in terms of machine learning and AI. That's not that's well known. And this is a key initiative to change that. So it's pushing within AI and within autonomous systems and software. And it's across these universities that are involved in this project. And the strategic instruments are, of course, doing research, pushing as hard as we can there. And then there is a fairly big recruitment package included, so including professors at all levels, 50 in total. And then there is a fairly big graduate school, so in total it's aiming for more than 300 PhDs, and out of those there will be at least 80 which is industrial PhDs. And also a fair bit in terms of platforms, actually building things or using autonomous systems in various ways, in particular together with the companies in that sense. So with that, I should conclude. So I've been trying, maybe not so much as I could, but I've been talking quite a lot about uncertainty, and you are well aware of that. So that was one of the really nice takeaways from me coming here, and also to get to know a few reasons why that might be useful, and also the fact that the best performance today is given by these highly flexible models and taming them in various ways, and in particular through deep learning or Gaussian processes. And then this project is allowing us to run a bit faster within this area in this country, I hope, over the coming 10 years. So thanks a lot for staying on and listening. That's a very interesting question. So the Lanczos iterations compared to conjugate gradients. Okay. No, so I did not know that, and I don't know, but I would be surprised if you can't use similar reasoning to at least investigate your question, for sure. Then. But I don't know the answer, I'm sorry. It's a good question. Now that's an extremely important question. So it's related on data, and are there any initiatives on how we actually generate and use and store data? So within the field that's discussed a bit, but I would not say that there are any major initiative in the field that I'm aware of. There is actually a Swedish company focusing on exactly this problem called Untitled. So that's probably the major initiative I'm aware of that's looking specifically at that question. But it's highly important, as you said. I mean, data is driving everything here. So, what do we do when, with all the data we get? But it's hard also to separate that question from the algorithms, since and the models, since it's so integrated. But I would say more could probably be done there. Yeah, that's a great question. So when would I use deep learning? When would I use Gaussian processes? So first of all, to do deep learning, you typically need a lot of data. So if you don't have that, you should probably not use it. Whereas Gaussian processes can be used with much fewer data. But still, so the basic Gaussian process is computationally super expensive. I should have stressed that maybe. It's cubic in the number of data points. But there are very good approximations to that. So in reality, in practice, that's not the problem. So for example, when we built the magnetic fields, we have hundreds of thousands of data coming in real time, and that is not the problem. We can do that. So it's fine. So but some time ago, that was a key issue, so to speak. But that's, I would say, more or less gone now. There's still interesting research to be done on that, but there is also a lot of practical tools that can be used. So in that sense, when you have a lot of data, I'd say it's super interesting to look at both of them. One good thing about the Gaussian process is that you get an uncertainty estimate. So so as we had, I mean, the MCMC dropout, for example, it was showed this morning, which I was glad to see that there's more to be done, and the ensemble methods are giving us something, but it's far from enough, I would say, in order to have a good probabilistic understanding of deep learning. There's definitely more to be done. Like you said, it gives something, and if that's enough, that's fine. But I see more opportunities there. Mm-hmm. No, that is an interesting and like a common question in a popular scientific setting. And it's when thinking about that, I'm spinning it around a little bit. So for example, if you are faced with that situation, hopefully you will never be, but let's say you are, what do you choose? How do you make that decision? Probably most of us will just be paralyzed and we don't know what to do, and something will happen. And if you survive and are asked to explain why you did whatever it is you did, you will probably not be able to explain that, because this is such an extreme situation. I don't think I would be able to be rational and make some kind of rational or ethically correct choice in that situation. I think something will happen, and hopefully something good or not too bad. So in that sense, I mean, a human being, I think, has a hard time dealing with that situation to start with. But and then another situation, I'm still not answering your question. I'm just talking a bit around it. And today, I don't remember, we have a camera there, but I'll say, so we have, I think it's 1.2 or 1.3 million people, somewhere around that region, that are killed every year in traffic accidents. And way more than that are seriously injured. And to put that in contrast, if you sum the number of people that are killed in wars and violent crime and so on, you need to double that figure to come up to the number of people that we kill in traffic. So when you think I think that is interesting, because we never, or that's why I take time to talk to you about this, because it's very seldom that we reflect upon that, especially if you think when you watch TV, what you see is typically some horrible war somewhere, and that's of course horrible, but still, if you think about the absolute number, we kill each other way more by in car accidents. So we have a huge problem already, the way we humans operate these 1-ton machines at high velocity very close to each other. So when you start thinking like that and seeing that one of the key reasons for accidents is actually that I, as a driver, am not paying attention for some reason. I get distracted or so. Whereas if you have an autonomous vehicle, that will not get distracted. And as of course you need to raise the bar and have something which is at least as good as we are. So in that sense, I see I think we have a huge problem already now, the way we have structured it. But we never think about it because, of course, we need to drive. But we rarely think about it. But I think it's the situation we have is really strange, actually. But then coming back to your question, this classic one, if we have a young, healthy person and an old person, yeah, and the car for some reason needs to kill one of them, which should it choose? It's a good question, but it's probably not exactly what's the situations that's going to happen. But if you want, you could start reasoning about what's the ethical thing to do, and I'm not sure we can agree on what that is, because it's a very hard question, right? It's not that is correct or that is correct. But you could come up with a solution and implement it for sure, but. No, but the ethical consequences and thinking about those, I think that's super important and we should do that. But I'm a bit surprised that we're not already doing it, so to speak, given what we are doing as we speak now as human beings. But we have sort of just accepted that because what else can we do? Yeah, that's what we do, right? As soon as you put yourself in a car, that's what you're doing. No.
Okay, maybe we should